In Slovenia, the country where I come from, we have a saying "Dobra priprava na delo je polovica uspeha." This would roughly translate to good preparation before work is half the success. Even though this proverb is much older than computers, it remains true for software development as well. One should carefully consider and define how to approach development, testing, deployment and other processes in making software, and NSO service development is no exception. When I was a junior developer working on my first NSO project, I didn't know that, and as a result my development experience was not very pleasant. The project was about migrating large interface configurations from end-of-life devices to the new hardware, using NSO as a migration tool. And my task was to develop a web portal on top of the NSO to enable the operators to perform the migration using simple user interface. It all started with me. I just built something simple, couple of drop-downs to select a device to migrate from an interface and then to select the target device, and that's it. In the next couple of months this grew into a proper web application and we were running into a bunch of problems. All of these problems were a result of poor software development practices. There was no common test environment that all developers we would use, so every developer was on his own, meaning that there were discrepancies between NSO versions, NAD used and other dependencies. In our environment we were only able to test on native devices, so often this resulted in errors only to be found when testing in customer physical lab. There were also no continuous integration and continuous delivery, so it was really hard to tell what version of the software works and which one has bugs. Today I want to share with you some tips and tricks I have learned over the years that will make your NSO development experience a delightful one. The one when developer can spin up his own playground with NSO and virtual routers in minutes, neatly packaged as Docker containers, where services are well tested and you are not afraid of deploys to production. Before we jump into the first tip that I have for you, let me quickly introduce myself. My name is Blaž Dolenc and I'm a software engineer at Flint SI, where a big part of our expertise is everything NSO and network automation related. Through Flint SI, I worked as consultant and developer at Deutsche Telekom for the past 5 years, and there I have the opportunity to work with some really awesome people, and a lot of what I will be talking about today is a result of these engagements. I'm a Cisco instructor, so I'm also involved in delivering and developing various NSO trainings and other learning materials. Okay, let's get to it. The first tip I want to share with you is kind of a low-hanging fruit, but it will bring you many benefits if you apply it to your project. If you are not doing it already, I really recommend that you start linting your Python code. So what is PyLint? If you don't know, PyLint is a static code checker, which means that it can analyze your code without actually running it. So it is a cheap way of checking for errors. It tries to enforce a coding standard and a coding style. So how to include it in a NSO project? In NSO we are already using makefiles to build your Yang models that are part of the packages. So why not use make to execute the PyLint too? It's quite simple to do so. So here we have a sample makefile for the loopback package. Add PyLint as a dependency to the all target, so that each time when you build your package, the pylint will be executed too, and your code will be checked. Then you just need to add a definition, so what this target will actually do, how it needs to execute the linter with the specified pylint RC file. So pylint RC file is like a configuration file that tells pylint on what kind of errors, warnings and conventions you want to have it triggered, and you can simply generate an RC file to start with using the pylint generate RC file command. Okay, so here we see the linter in action. So in the output you can see that here it detected some problems with our loopback package code. There are different types of messages that pylint will display. We have errors, so these are messages that indicate critical issues that are likely to cause problems or errors in your code. So these are like syntactic errors, some undefined variables that you're trying to use, and so on. Then we have warnings, so these messages point out potential issues or code smells that might lead to problems, but are not as critical as errors. And then we have conventions that relate to coding style and coding convention recommendations. These help you ensure that your code adheres to a consistent style, making it easier to read. So let's see an example of one of the detected problems in this output. So here you see that we are not correctly ordering our imports. So how to fix that? The IP address import should become first, since this is a standard library import, and other third-party imports for NCS stuff should come after it. So this is the convention that the pylint enforces. Second tip I have for you is you should invest in good development and test environments. So what is a good development or test environment? I think that good metric for how good your environment is how fast you're able to onboard a new developer. Is the process like long, and if it takes a lot of manual steps of installing dependencies, getting this virtual machine there and install this thing there. So if that's taking a really long time, then you have a lot of room for improvement here. So you should strive towards the environments that are easy to set up, and most of the things, development environment should be defined once, and then everyone should be able to easily use. The first question that usually comes to mind when we are talking about NSO development environments and testing, the environments for testing, is what kind of devices to use. NetSim usually comes to mind, and it is a great tool to start, but it's lightweight and easy to set up, yes, but on the other hand it's also limited, so the real device might reject the configuration that NetSim happily accepted, and there is no real operational testing possible. So it is something, but usually we want something more. Physical boxes on the other end are the real thing, and you can test everything you can imagine with them. But for everyday development, usually they are too expensive, and you probably won't be able to afford to have a full physical lab for each member of your team. It's also trickier to have them in a consistent state over many test runs. So in the middle there are virtualized routers, and we prefer to run them in a form of Docker images, because you build them once and then you can easily transfer them around using established tools that are part of the Docker ecosystem. VRNetLab enables you to run router images in a form of Docker containers, and also takes care of stitching them together so that the connectivity between interfaces works as expected. Lately there is another prominent project called Container Lab that is also gaining traction, and it integrates with VRNetLab, so it supports all of the devices that VRNetLab does, and in addition it supports containerized network operation systems. So it is a nice, maybe a bit more user-friendly alternative to the VRNetLab. So yeah, check it out if you are starting on your virtual router testing journey. What are we usually using is a combination of all three options. So first thing we do is we split tests between full and quick test environments. And the difference is that full test environments contains larger topologies with more devices included. On the other hand, we have quick test environments that usually have 1 or 2 devices and are faster to start and can run on your laptop. Then we also have NetSim versions of the environments. While full version spins up VRNetLab devices, full NetSim of course uses NetSim. So based on what you are working on, you then pick applicable test environments. Sometimes it is enough to just do a quick NetSim one, or if you're just doing some refactoring of the service code. While for other tasks, where for example you want to collect state from the device, or when you want to test if the pings are working and if the BGP sessions are up, then you need to spin up the full test environment. And this will usually require some kind of development server with quite some RAM and CPU power. So let's take a look inside a full test environment folder. So what does it contain? So this, what you see here, these test environments, they are folders in all our projects where we are developing NSO services. So what each of these folders contains. We have a service config that configure test service instances, and this in turn creates device configurations. So here you specify what service instances you want to test, what configuration you want to do during the configure part of the test environment. The topology JSON defines how our test topology looks like. So this is input for VRNetLab that based on this produces the needed scripts to start the virtual routers and also stitch them together as you see in this point-to-point section, which defines that the P device is connecting to the CPE1. We are relying on makefiles to drive our testing. So here you see this test.makefile, and yeah, we have start, configure and test targets in all of these test environments. So start target takes care of starting virtual or NetSim devices. In this case, since this is a full test environment, it starts VRNetLab container in a form of Docker. NSO is also started inside the container, as you see in the last line of the start target. Configure target then loads the service instances for testing, and the test target takes care of checking for things like if service nano plans have progressed to the ready state, and they perform various operational checks like pings, if BGP sessions are up, SLA testing. All of this then happens under the test stage. So how good we are with these development environments? So based on this developer workload, I would say we are doing pretty well, since when a new developer starts working on our project, usually he gets his dedicated development server, and all he needs to do there is he needs to git clone the repository that he will work on, and then using the make build target, this will produce the NSO image with local packages. So any changes that you do there will already be reflected in this build NSO image. Then you select the environment that you want to run and use the test environment full start command. So pull in via netlab images and start the topology, and also start the NSO out of the image that was built in the previous step. So we have the topology up and running, neatly connected. And with the configure target, we then test this environment we configure them with the test service instances. So after a couple of minutes, depending on how fast the virtual routers are, you end up with configured environment and you can start hacking on it. If, for example, you're working on your laptop and don't have the resources for full VR topology, just use the test environment full NetSim topology instead. The make targets are all the same, so really easy to remember how to start each environment. What is great with this approach is that the same test environments are also running in CI, so there is no separate CI environment. It's the same environment that you use for development and local testing. The same test environment is then executed on the CI CD runner. It's just that now the build, configure, start and test target are executed by the runner. So for every commit to the repository, NSO Docker image is built with the latest version of the packages. Then all test environments are started, test gets executed, and if all of the tests successfully passes, then we can immediately deploy to the lab. So if this is the main branch, this is what usually happens. And yeah, you can also either automatically commit to the or deploy to the production too, or have this as a manual job. So if you want to learn more about such awesome test environment, go visit this NSO Docker project on GitLab, and you'll learn and find there all the building blocks to build such an environment on your own. Tip number 3 is a really good one. So we all know that NSO can do great things really fast in your network. What can NSO also do is it can do really bad things really fast if you make a mistake and push maybe unwanted configuration towards the devices. So I think that having good control over your configurations is a really important safeguard against unwanted changes and such catastrophes. So inside the test environments that I have shown you earlier, we also have 2 additional folders. One is called expected and the other output. So expected folder is for good known device configuration and is checked into Git, while the output folder is there to store configurations of the current test run and is ignored by Git. In this test.make file, we have 2 additional targets that I haven't shown you earlier. So there is this save output target. So after every test run, we save the output, usually all the devices output, but often the service outputs too, if we have more complex hierarchy of services. And then there is the check diff that does the comparison between the expected and between the output folder. So after every test run, we would populate this output folder with devices XML. So this is NSO CDB output of the whole devices tree. So all devices configurations ends up here. In the expected folder, you store the verified working configuration. When you start out, this will probably be just a copy of output devices XML, but later on you're carefully examining any differences that pops out between the two, and you need to keep the expected configuration in a working state. After output is saved, we executed the check diff target to compare output with expected config. If there is a difference between the two, test will fail. So this target will fail, your test will fail, so you need to decide if the diff is expected or not. If yes, you need to update the expected devices XML. Otherwise, you need to fix your service or service configuration, so service code, or however you do the testing, so that this output will be as expected. But the overall idea is that there should not be silent config changes that goes by unnoticed. There is another benefit of this approach. So let's say you're adding BGP loopback interface configuration to the existing service. Usually this means that you will check out the main branch and implement your changes in a separate branch. So you do this commit of adding BGP address to loopback interface, and this will produce some new configuration that the check diff target will detect it. So you'll probably need to do another commit where you will update the expected device config, so copying over the output into the expected folder, so that these devices XML files are in sync again. So when you open a merge request, so to merge back into the main branch, so you will open a merge request for your colleagues to review. Now you will not only include your code changes that you did, or your template and Yang model changes you did to the service package. The merge request now will also include how this code change has affected the device configurations. So when now the device config is also part of the review process, and reviewers looking at this change can quickly see if there is something wrong with the produced configuration and comment accordingly. Another example of this preventing bad things to happen would be when you are refactoring existing service packages and suddenly some config is gone from the device because maybe you made a tiny mistake in the template when you are referring to your Yang model, or you forgot to set some variable from the code. Quite easy to miss without storing expected config, so I really recommend you to start doing that. My last tip is that you should not reinvent the wheel. What do I mean by this? We as software developers are often inclined towards implementing everything on our own. So let's say we have this NSO service package. We need functionality to declaratively add a device to the NSO as part of this provisioning process. There is this perfect open sourced package that does exactly what we need, but often instead we rather go build something on our own for a variety of reasons. So either the existing solution seems too complex for us and we don't really understand it, or we just believe that we can do better. Sometimes it will work out, sometimes it doesn't. In this example, you will need to learn the hard way all the details around adding a device to the NSO. So if you want to properly implement that, and since somebody else already went through all of that, maybe it makes sense to use existing packages. So here I would like to direct you towards some packages that are freely available and can help you on your automation journey. First one is Device Automaton that adds devices to the NSO in a declarative way. One should say that this is something we all need and it could really be part of the NSO, but yeah, it's not, and yeah, Device Automaton helps you with that. It comes with loads of nice features also, so it supports multiple management endpoints and can also monitor them and switch to the working ones if needed. It can automatically detect device type and the most suitable net, and it takes care of out-of-sync scenarios and other features. So check it out, it's also on the NSO developer group on the GitLab. Next one is BG Worker that enables you to run background worker processes in NSO. Often you'll find the need to do some periodic task to run something periodically, like if you are pulling devices for operational state or if you are checking if services are in sync. BGP Worker can help you with that. It works well with high availability, it handles restart for you and config changes, so a really nice tool if you have a need for that. I already mentioned NSO in Docker, but since it's really helpful if you want to start running NSO in container, I'm mentioning it again here. So it's not just used to build Docker images, but there is much more included in this repository. So there are skeletons for building network element drivers as Docker images that you can then compose together in a project. There are make files with reusable targets. There are even GitLab CI definitions to get you started with awesome testing environments. While this one might be a bit overwhelming at first and you really need to grasp all the concepts and how all composes together, I think it's really a worthwhile investment. So if the tips and practices that I shared today have got your interest, I have something for you. So with Cisco we have prepared a lab that showcases some of the concepts that I have shown here. Visit the link here and this will get you VS Code NSO environment within the browser, and you then have inside a step-by-step guide on how to implement good development practices on your own. So yeah, kudos to Cisco for this really nice environment. It is on demand, it's quick and really nice to work with, and yeah, I think you will learn a lot with this lab. So I would like to thank you for listening, and I hope you have learned something useful today and that the tips that I shared will help you move towards a more delightful development experience. Thank you.